So I'd like to thank the organizers for inviting me. I'd also like to thank them for putting me on the second day. Maybe during the rest of the week I can learn some things instead of writing slides. So originally I was asked to talk about machine learning challenges in complex multi-scale systems, which I'm sure is very interesting, but I don't know what it means, even though I helped organize a workshop at Technical University of Munich on this. So you will hear about what I know, which is Lattice QCD. But I've tried to pick the parts of it that I hope interest you. So here's the outline. I'll remind you of some of the great stuff that we've done in case you're not experts. Then I'll talk some about the basics of lattice gauge theory, a little bit on software, then something on the random number generators that create quantum chromodynamics in a computer, something on solvers for quarks. Then since I don't know enough to say something sensible, I'll speculate about how maybe you could help us in these past two topics. Then something on Bayesian curve fitting, because that fits in with machine learning, and then some upcoming physics challenges. OK, so you all know QCD starts with 3 colors of quarks, 8 colors of gluons, and it's described by very few parameters, alpha s, a phase theta, and the 6 quark masses. This phase theta, I'll get back to it, is the source of the strong CP problem. And out of this very simple thing, you get all of hadronic physics, all of nuclear physics, a whole lot, even jets. This theta has to do with the fact that non-abelian gauge fields have a non-trivial topology. If you imagine that the field goes to a pure gauge, or in physical terms, 0 field, this gauge transformation at infinity can wrap all the way around the sphere. So this funny combination could be written this way in terms of the gauge transformation at infinity, or this way in terms of the fields, is an integer. So this is sometimes called a Chern class. So whenever this comes up again, I have a picture of Professor Chern. So as I said, this leads to the possibility of strong CP violation if theta, a coupling multiplying this topological charge, is different from 0, and also if none of the quark masses is 0. It's usually phrased as the up quark mass being 0 or not, because that's the smallest one. And we know now from Lattice QCD that M up is very far from 0. And that means that if you add something that comes from QCD to something that comes from the quark mass matrices, which we think comes from the weak interactions, Yukawa couplings, that sum has to be 10 to the minus 11 from the neutron electric dipole moment, which is a pretty mind-boggling puzzle. A striking feature of QCD is that the hadrons have masses. One of the original aims of Lattice QCD was to calculate the hadron masses from first principles. This is now something that can appear in textbooks. So what we have here are various mesons, various baryons, and these are all calculated to within a couple %, except perhaps the eta prime, and also heavier mesons like Ds and Bs. The Bs here are offset just to bring them down onto the chart. And what you see here are different colors corresponding to different groups who have done this. These different groups use different details in the formulations, and then when you get rid of the lattice, taking the continuum limit, they all agree. People now go on to do this for excited states and even try to disentangle mixings in the isoscalar sector. We do a lot of work in flavor physics. So here are 2 tests of the unitarity of the CKM triangle. All of these sums should add up to 1. The last element from B physics is negligible in this sum. So these 2 should add up to a straight line. And you see that the intersection is here within about a sigma of unitarity. Here's another case for the second row. Again, maybe 3 sigma off. It's interesting to note that in the experiments are ahead of us here, though we are not very far behind. Here the experiments have a way to catch up with us. OK. This flavor physics is also a huge enterprise. I don't expect you to see all of this, but these are averages from a group called the Flavor Lattice Averaging Group, who aggregate results and give them grades. That's what the colors mean. And so you see that, again, here in flavor physics, there are many groups doing many things, and all of these things can be used to pin down various parts of the CKM matrix. These people in FLAG work very hard, but if I blow up the one in the lower left, while they are reviewing, there are people who come along and get results that render their averages obsolete. So this is also something that is not standing still. Here's another example for LHCb, because no one mentions LHCb, right, Mike? Here's a comparison of a flavor-changing neutral current. This band is what comes out of Lattice QCD. These are data from all the various experiments. You can't see the lovely LHCb data with small error bars because all the other experiments have large error bars and cover them up. But to make a long story short, both of these are in some tension that you're not allowed to get excited about, right? But theorists are so desperate for anything beyond the standard model that this is considered very exciting. Okay, so a synopsis of this appetizer is that non-perturbative QCD is rich. I've just talked on things on particle physics. There are things in thermodynamics, for example, relevant to the heavy ion collisions. There are lots of things in nuclear physics that is copacetic with the JLab program and so on. The low-lying hadron spectrum agrees with experiment at 2% or level or better. Excited states are more challenging, but progress is moving along. Quark flavor physics is also now in the sub to few percent uncertainties, and it includes several validated predictions. That means that we calculated things before they were measured in the lab, and these things validated us. People still say, when are you going to do this? And the answer is we did it about 12 years ago now. There's even a prediction of the BC star mass, which is yet to be seen in experiments. Okay, so now I'm going to tell you how we do this, focusing a bit more on the algorithmic aspects. So the whole problem with quantum field theory, if you have infinite space-time and a continuous space-time, is that the number of degrees of freedom is uncountably large. It means it's larger than the number of integers. And that's where the ultraviolet divergences come from. So if you discretize space-time, think of aggregating all of the degrees of freedom in some sort of cube down to one point and associating it with these blue dots. We call them sites. This is actually where you put quarks. It's where you put scalar fields like the Higgs if we were putting them into the lattice. And then the gauge fields live on the connections between these two sites. We call them links. That is the way to preserve gauge invariance. Anyway, an infinite lattice has countably many degrees of freedom, and so it regulates the ultraviolet divergences. If you want to do this on a computer, you also make the space-time volume finite, and then you have a finite but really, really big number of integrals to do. This is the general expression, Feynman's functional integral, if you like, so the expectation value of some blob is this blob with this weight integrated over the quarks and over the gauge fields. We call the gauge fields U. You can do the integrals over the quarks by hand, so we do that. And then the fermion part of the action becomes this determinant of the Dirac operator plus the mass. On a lattice, this is a large, sparse matrix. And then if there are any pairs of quark fields in this blob, you replace every possible pairing up with a quark propagator from one point in the lattice to some other point. Then we do that by Monte Carlo, and I'll get back to how we do that later on. So there are some algorithmic issues. The lattice has some size. I should have shown it here. So you have n sub s along a side, n sub 4 in the time direction, usually made very long. I'll explain why in the next slide. Lattice spacing is called A. The side of the box is called L. I usually call this extent in Euclidean time L4. Sometimes it's called T. So we're in 4 dimensions. That means that the memory goes up very rapidly just because we're in 4 dimensions. Eventually, we want to take A smaller and smaller, so we do, of course, a lattice spacing, a fine, and then a finer. And most of the calculation I'll talk about based on my work, we have 3, 4, or 5 of these different lattice spacings. So there's nothing you can do about it because we live in 3 plus 1 space-time dimensions. The Monte Carlo evolves the whole gauge field through some CPU time, which I'll call tau. The 4 comes in also because we're in 4 dimensions. And then the algorithms are naturally slowed down. This is called critical slowing down. And there is great effort to get this critical exponent of the dynamical simulation down to 1. It's typically actually 2. Similarly, what we have to do to get these quark propagators that I mentioned just before, we have to solve a linear system of equations that also slows down as you take the continuum limit with a power of 1 or 2. Some recent algorithms claim that you can get this p down to 0. We'll see if that holds up when you get to even larger lattices closer to the continuum limit. Then we also work in imaginary time. So this time t is the time you experience. We multiply it by I. That means that instead of having is the way Feynman would have it, you have a minus sign here. That means that this is a positive weight that can be interpreted as a probability. If you're looking at static quantities like the mass or a transition matrix element mediated by an electroweak current, that's not a problem. There's some other things you might be interested in where it would be a problem. Also, if you take the temporal extent very short, it turns out that this expression boils down to the quantum canonical ensemble. So this is how thermodynamics is done. Okay, this H is a Hamiltonian corresponding to that action. It's the eigenvalues of this Hamiltonian, which are the hadron masses. So to compute the masses and matrix elements, this is really all we do on this slide. So we have a computer generate this left-hand side. So in this example, you have a B meson created at time 0 and annihilated at Euclidean time x4. Then there's a theorem that says that this is a sum over the B meson and all its radial excitations of some matrix element connecting the ground state of QCD to the B meson times e to the minus mbn x4. This minus sign comes in again because we're in Euclidean time. So you can fit this to a sum of exponentials, and then you get the mass out. I'll come back to this. If you want a matrix element, so this now is the BU electroweak axial current. It can annihilate the B meson. Then you've gotten these blue things from the top line. This is the way you get the decay constant. This is the part of QCD that would enter into the decay B to tau nu. Then there can be other matrix elements where you want a 3-point correlation function. This looks something like this. The example I wrote out is BB bar mixing. You could also have a B meson here and a pion here if you wanted to calculate the decay B goes to pi L nu, which is used to measure some of these CKM matrix elements. So what I like to say is that you need a supercomputer to compute the left-hand side, and everybody knows that. What is sometimes underappreciated, particularly at funding agencies, is that you have to hire some superhumans to analyze the right-hand side. So whenever you see a picture of someone in these slides, well, except for Professor Chern, it's a superhuman who has been doing these analyses. So the steps are write a random number generator to generate a sequence of lattice gauge fields. Solve this to get this equation to get the quark propagators on these gauge fields, and then fit the correlation functions to get masses and matrix elements. Okay, so you do this on one lattice spacing, then you do it on the next lattice spacing. Maybe you don't have the bare parameters tuned up exactly right, so you have to repeat it for various choices of the bare parameters. Maybe you're interested in a decay that has some momentum of the final state hadron. You have to do it for several values of the momentum. And so you have to do this over and over and over again, and then combine all the data, numerical data from up here, to get things that mean something to somebody, for example, a mass in MeV. Oh, you must be kidding. All right. Who cares about software? OK, so here's the equation again. And there are billions and billions of integration variables. The action is extensive in the language of thermodynamics. So that means it scales with the space-time volume. So let's say, for the sake of argument, free field has action 0. Then e to the minus 0 is 1. But suppose at each point you have 0.2 worth of action, which is actually typical. Then you have e to the minus 0.2 times billions and billions. That's a small number. So the only way to do it is Monte Carlo integration with importance sampling. So you have a set of these gauge fields. This is this blob with quark propagators put in it as a function of a set of these. And these things are generated with the weight in here, exponential the action and the determinant that comes from the quarks. I didn't mention the physical interpretation of these are C quarks. You know, gluons can annihilate and produce up and down and strange and even some charm quarks. And the propagators in here correspond to valence quarks, the ones that actually decay. OK, so how do we do it? So we have a Monte Carlo Markov chain. In the old days, this determinant was much too expensive. So old days really means the previous century. And then local algorithms were good enough, and you could just order all of the gauge fields in some way and then update them locally with metropolis or heat bath algorithms. But this object can be written also as a weight. This is also a non-negative number, so you can write it this way. But this leads to something very non-local, right? You have a sparse matrix, but if you try to take its logarithm, you get something that's spread out all over the place. So that led, actually, a long time ago now, to the search for global algorithms that update the whole lattice gauge field in one fell swoop. So all billions and billions of variables at the same time. One idea was to steal what chemists do when they move molecules around. This is called molecular dynamics. It's also, in thermodynamics speak, equivalent to the microcanonical ensemble. And so they use Hamilton's equations to move things around because they've got an actual Hamiltonian. That amounts to inventing some fictitious momenta to go with the variables that we're interested in moving around. This is claimed to have this exponent I talked about equal to 1. But since it's a kind of classical system, we don't know whether it's ergodic. In particular, there can be modes that have roughly the same frequency, and they just sort of go around and around in circles. And you're trying to explore some enormous space, so some of the degrees of freedom go around in circles. You're not doing a very good job of exploring. So a way to avoid that is to use another kind of equation, the Langevin equation. This is a diffusion equation with some random noise added to it. So it's certainly ergodic, but naive arguments say that it's much slower. This critical dynamical exponent is 2. So then the idea came along to combine the best of both of these ideas. And of course, that's called hybrid, right? Whenever you combine two things, you call it a hybrid. So it's noise plus Hamilton's equations. And again, the argument here is that it has z equals 1, and the argument from here is that it's ergodic. I'm about to cast dismay upon this and then rescue it. OK, so these algorithms or their variants, I've learned, are used in machine learning, for example, to examine the posterior probability distribution. So you're trying to fit many different variables. Some of them are steep when you look at the log likelihood. Some of them are not steep at all. and you want to try to figure out where you are in this probability space. In fact, at this workshop in Munich, someone was asking me what I know about hybrid Monte Carlo, and I said, don't ask me, the inventor is standing right here. So I'll get back to what hybrid Monte Carlo is in about a slide. So consider the action if you are interested in lattice gauge theory. Consider the potential energy if you're a quantum chemist. Consider the cost function if you're looking at a posterior of some complicated Bayesian analysis. Call whatever that is V, just to have one unified notation. Call the degrees of freedom, be they lattice gauge fields, fit parameters, or the coordinates of a molecule phi. So you form a Hamiltonian for each one of these phi. You introduce conjugate momenta, call them pi. And then these are Hamilton's equations. You discretize them just like this. As I said, there's a danger for nearly periodic modes. So this hybrid molecular dynamics, every now and then, says that the momentum is going to be some Gaussian random noise. I'll use Xi for Gaussian random noise. This is the lambdth time you introduced it, and the I labels all of the different coordinates. Then you move forward half a step. Then you go alternating each one n-1 times. Then you do this one last time on phi, and you do the last half step on pi. I've gathered that you like pictures, not equations, so just forget about the green box. Anything that is reversible will do. In fact, part of the science is to figure out better algorithms. I didn't tell you how you get a new phi from the previous one. That is just by doing this. And then hybrid Monte Carlo, you might know it as Hamiltonian Monte Carlo, consists of applying a metropolis step to decide whether or not you accept this. And the metropolis is applied to the change in the Hamiltonian at the beginning and the end of this trajectory. OK, so you can estimate step size errors. I'll skip that. The spectrum of these things is often quite wide. So it certainly is in lattice gauge theory. It is in many probabilistic things where you have gradients of vastly different size. It turns out that the trajectory length is optimized in something that is geared by the largest of these things. So that would be the steepest gradient if you're doing Bayesian statistics. And that means that the shallow directions don't move very far. So it's actually not as efficient as you thought. And to make a long story short, it's effectively z equals 2 and z equals 1. There's a remedy of this, which was well known but then forgotten even by us, which is that you can lengthen the trajectory to be dictated by the smallest, in other words, the shallowest direction in your space by refreshing not after some fixed length in CPU time, but after some random time chosen with the probability of the lowest frequency times the step size. So that means that every mode goes around in a circle sometimes, but no mode goes around in a circle every time. So it remains ergodic. You can take the trajectory length large, so you move even the slow modes a long distance in configuration space. OK, so remember QCD. The non-local action of quarks on the gauge field is this expression I showed you before. And the reason for showing you the derivatives before was to let you know that what we really need in doing this evolution is the derivative of this traced log. And so that's the trace of 1 over the operator. This can be estimated by introducing some more Gaussian noise, not the same as the one before. And then you only need to solve this equation. Typically, this Xi is regenerated at every one of those Monte Carlo steps along the trajectory, and it's the most demanding part of lattice gauge theory. Look at this if you're bored sometime during the conference. So we need to solve this also for valence quarks. As I said, this is a sparse matrix, so people use Krylov solvers. It also slows down based on the ratio of the eigenvalues of this matrix. And the lowest lying modes are very non-perturbative. They come about when the gauge field topology is complicated. They force very low lying modes in the Dirac operator. And those modes slow down any algorithm to solve these equations by an enormous amount. So the solution is something we call deflation, which is to project out the first few to several modes. So this is just an equation saying that if you want the inverse of this, you can write it as something where you subtract out the deflated modes, and then you add back in the deflated modes here at the end. I'm sure I wrote DEFL, but my computer has taken to spell correcting everything, so I don't know. Okay, so something that claims to remove all of this critical slowing down. In other words, you can make the lattice spacing smaller and smaller without needing more time to do it, is called multigrid. There are numerous groups working on this. Actually, this is someone who works for NVIDIA now. These two, Brannick and Frommer, are applied mathematicians. And we couldn't do this in the past. We had to figure out various tricks, like how to go from this very rough field to something that is smoother in a gauge covariant way before you could project down, again, in a gauge covariant way to a coarser grid. OK, so 0, OK? Oh, you're right. Rampant speculation. We run these simulation programs literally for years. And they're on a computer. And we spend a little bit of time figuring out how to optimize them. But we don't want to stare at the computer all the time. We want to analyze things and do physics. It would be really, really neat if we could teach the simulation to learn from what it did 3 months ago and do it faster in the next 3 months. So if you have any ideas on that, please let me know. Curve fitting is boring. Oh, I should mention this guy is now in data science. OK. OK. So in the time that doesn't remain, I'll tell you about a couple future challenges. So first of all, precision. So here's an upcoming result for these B-meson decay constants. They're going to be about 5 times more precise than they were just a year ago. This means that future work for flavor physics is going to need isospin effects. Massively up, different from the down in these C quarks. We've neglected that today. We have to put in QED if we're going to do any better than this. Success also attracts demands. There are many new needs in particle physics and even more in nuclear physics, and I'll just talk about a couple. So hadron structure applies to both. You'll be interested in the parton distribution functions inside the proton. Here is a recent innovative way of obtaining these in lattice gauge theory. This filter and derivative are 2 different ways of processing the numerical data compared to a CTEC set in the gray error band. This is the first time this has ever been done, and right out of the box, it's getting something that looks very much like what you get when you do the analysis phenomenologically. So this is something that could help, particularly out at large x, where the relative error of these things is large. Neutrino physics needs things like the axial vector form factor. Here in blue is a recent calculation. Let's not talk about the other stuff because of lack of time. Since we're in Seattle, we have to talk about muon G-2. It also dovetails with the end. To make a long story short, the 2 largest contributions to the standard model uncertainty are hadronic. If you have good eyes, you can see the electroweak uncertainty. The electromagnetic uncertainty is even smaller than this brown line. So we have to reduce the uncertainties from these 2 hadronic contributions by about a factor of 4 to meet the demands of the new experiment. And these guys say all the time, they really need us. They are banking on us to do this. So this is not easy. This is harder than anything that I talked about already. But there's progress being made. There's a first 2 complete results, one already with an uncertainty that is small enough, and since it fluctuated on the low side compared to other ways of determining the light-by-light contribution, it's about 3 sigma from what you would expect from no new physics. The other contribution looks like this. It's called light-by-light scattering because there are photons here, here, and here. There's been great progress from the Ricken, Brookhaven, Columbia collaboration. They can now calculate something with a statistical significance that is nothing to sneeze at. This result has huge finite volume errors, but they figured out how to get rid of the finite volume errors in a very clever way. All right. I think numerical lattice QCD could be a great element of this conference. The machines and algorithms subcommunity at our conferences is pretty large, and it includes applied mathematicians. Some of my friends have done pioneering work on algorithms, hybrid or Hamiltonian Monte Carlo, also on hardware. Lattice people were the first to use GPUs in scientific computing, as far as I'm aware, at least in high-energy physics. And there's probably also a lot for us to learn from you guys. Thank you.
Thanks a lot.
That's supposedly the space station. I don't know if you saw this.